Hi there. I'm not going to go on a big dissertation about all the formulas or all the definitions that you need to know about electronics. I'm just going to go over a few concepts, those being Ohm's law and its three variables, being voltage, current, and resistance. We'll talk a little bit about power and watts. We'll talk a little bit about conductivity and possibly some Joule's law thrown in. So let's talk about Ohm's law first. If there's one formula that you want to learn in electronics, it's this one. It's Ohm's law. As mentioned earlier, we got three variables in Ohm's law. We got voltage, we've got current, and we've got resistance. Voltage is the amount of pressure that pushes charged atoms through a circuit. Most analogies use water to describe it. Think of garden hose versus a pressure washer. Obviously, the pressure washer has the higher pressure, and the pressure washer would have a higher voltage, right? It's measured in volts, and it's named after Alessandro Volta, who invented, amongst other things, the electric battery. In circuits, it's designated with the letter V. Current, on the other hand, is the flow of an electric charge, usually of electrons, through a conductive material such as copper wiring. Using the same water analogy, use the width or the diameter of the hose. The wider the diameter, the more water that will flow through it. The unit measure of current is the ampere, or amp for short, and it's named after French physicist André-Marie Ampere. It's designated with the letter I most often in circuit diagrams. Resistance, which is a third variable. Resistance, or resistors, slow down or inhibit the flow of electrons through a circuit. Using that same water analogy, think of a small pebble, for instance, stuck in the hose. It'll block the water flow, it'll inhibit the water flow, so it'll resist. The larger the pebble, the higher the resistance. Resistance is measured in ohms, designated usually by the letter R in circuit diagrams, and it's represented by the Greek character omega. It's named after German physicist Georg Ohm. So let's go over to the formula. Okay, the easiest way to remember the formula for Ohm's law is remembering this triangle. V for voltage, I for current, R for resistance, V over IR. In mathematical terms, V equals IR, or I times R. If you want to know the formula for current, you just look at the I, and what does that equal to? V over R. And R, you guessed it, V over I. Let's use an example here. Let's draw a simple circuit. We have a battery, we have a resistor. It's a 9-volt battery, and the resistor is, say, 100 ohms. What is the current of this circuit? So I equals V over R, which equals 9 over 100, which equals 0.09 amps, or 90 milliamps. Let's have another example here. Before we get into the example, just a quick little blurb on LEDs. So the takeaway on this LED is the two leads coming out from the bottom. We have a cathode, we have an anode. Cathode positive, anode negative. This is a diode, light emitting diode, so current flows in one direction. That is, the positive lead has to be connected to the cathode, and the ground has to be connected to the anode for it to light. Reverse those wires, the LED won't light. We have a battery designated by those two lines, plus and a negative, flowing into a resistor by that jagged line down to an LED. Symbol for a diode on an electric circuit is a little arrow with a line in front of it, as you can see in the image here. For an LED, which is a light emitting diode, you add a couple of arrows pointing upward, which designates the output of light from the diode. So we have a 9-volt battery, 3-volt LED at 20 milliamps or 0.02 amps, and we need to calculate the resistor. Let me quickly explain voltage drop. Voltage drop is the loss of voltage in a circuit caused of the flow of a current through a component, such as a resistor or an LED, right? So the voltage applied to this circuit is really the sum of all the voltage drops, right? So we have a voltage drop of 3 watts of the LED. We need to calculate the voltage drop of the resistor for the circuit to use up all the voltage. I hope that makes sense. So in this example, R equals V over I. Voltage equals really the volts coming out of the battery, which is really the volts coming out of the power source. In this case, it's a battery, so we have 9 volts, less the 3 volts that is being consumed by the LED. So the voltage drop of the LED is 3 volts. So therefore, the voltage drop of the resistor must equal 6 volts, right? 9 minus 3 equals 6. So we have the V. We have the I, which is 20 milliamps, which is 0.02. So R equals 6 over 0.02, which equals 300. So the resistor that we need in this circuit is a 300 ohm resistor. Now let's see that in real life. Okay, medium breadboard. We have a positive column and a negative column. This is called a power bus. When a power source is inserted into any one of these holes or slots, this whole column is connected via a metal clip. So when we take this battery, which I've attached some jumper wires to, when we plug in the positive end here, the whole column will be connected to the positive lead of the battery. Similarly, on this side, we have the same thing. They are isolated. These two columns are isolated. They're not connected. However, we can connect them by getting to another jumper wire and connecting the two columns together. So therefore, this entire column, this power of the power bus, and this column of the power bus, the positive, are now attached to the battery and are connected to the positive bus, to the positive lead of the battery. Similarly, it happens to the negative side. The rows, we've got 30 rows, right? And we've got 10 columns here. So these are the terminal buses. So row 1, A, B, C, D, E, are connected together. Row 1, F, G, H, I, and J are connected together. Similarly, row 2, 3, 4, and all the way down to 30. So therefore, if we take a jumper wire connected to the positive, let's add it to row 10 in the first column A. Therefore, each of these 4 other slots in row 10, B, C, D, and E, are connected to the power. We can also take another jumper wire and add it to row 10. F, G, H, I, and J are now also connected to the positive lead of the battery. So we have this entire column, and all of row 10 is connected to the power lead. It's connected to the positive lead of the battery. So let's set it up. We'll get the battery. Let's put it on this end. And I'm going to do my multimeter. We'll use the left side, positive to positive, ground to ground. We'll put it anywhere. Doesn't make a difference. All right. Just for demonstration's sake, I'm going to add a pin here. In row, in any of these rows. And we'll go from positive to this row 4. We'll go and we'll go the ground to row 20. So anywhere on the bus, anywhere in this row. So what we should have here, or what we should see, is 9 volts when we connect these two together. Let's see if I can get this all in. So positive and negative, keep an eye on the multimeter. And we have 9.14 volts coming from this battery. Okay. Let's keep that there. Now from our example, we used an LED, shown here, which was 3 volts and 20 milliamps. And we had a 300 ohm resistor. Not sure if this is 300 ohms. Let's check. Resistors have these color bands wrapped around it. And given the color and the number of bands, you should be able to determine the resistance of the resistor. However, I can't tell. The bands are too small and I'm a little bit colorblind. So I don't know if that second band is black or brown. So what I usually do is use the multimeter to determine the resistance. So keep an eye on the multimeter. What we have here is a 480 ohm resistor. It's measuring 473, but out of the package it's 480. What we want is a 300. So here's a couple of other resistors. Let me find it. We have a few other resistors. I'm not sure what they are. This is a 200 ohm. 468. 328. This will do. What do we want to see? We want power to resistor. We'll go positive to resistor. It doesn't make a difference if the resistor is before or after the LED. So we'll go to insert it into power, and we'll put it anywhere in row 16. Here's the LED again. Actually, let's use this LED. So what we need is the positive of the LED to the resistor and the negative to the ground. So we have, and there we go, lights up. And we have the circuit as demonstrated in the previous section. Now what we said, this is a 3 volt LED. What if we add 9 volts to it? How long will it last? Let's find out. So what we'll do is we'll remove the resistor. And let's add another jumper cable. So we'll go positive. So we had, you saw that? So sorry about that, my hand was in the way, but you may have seen a small flash of light. So what happened was LED lit up and instantaneously blew due to the overload, right? It's a 3 watt LED, adding 9 volts to it, it's going to cause the LED to... Back to the blackboard, or the whiteboard. Whiteboard, blackboard, chalkboard. Let me show you one more thing. So what's happening here is we have a 9 volt battery, this of which the LED is taking up 3 volts. Therefore, the resistor must be, let's call it consuming 6 of the volts. right? So the 9 volts comes in, resistor takes up 6 of it. The LED takes up 3 of it. And back to with 0 voltage, right? So that's how it happens. So let's just take a look here. There you go. So you'll see the resistor is consuming 6 volts. Quickly on power. Power is the rate electrical energy is transferred by an electric circuit. Simple enough. It's measured in watts, designated by the letter W. And if we're looking at DC circuits, which we are, watts equals V over I, which equals voltage over current. 1 watt equals 1 joule per second. I'm not going to go much into joules. Really, a joule is a unit of energy or a unit of work. We will talk briefly about Joule's law. The watt naturally is named after James Watt. He was a Scot. He was an engineer. He was a chemist. And through his work on the steam engine was really fundamental to the onset of the Industrial Revolution in the 1700s. So there you have it. Okay, let's talk briefly about conductivity. Okay, conductivity. Conductivity is the ease that an electrical current passes through a material. Think about copper wiring, right? Unit of measure is the Greek letter sigma. It's a little circle with a little curly thing on top. You increase the resistance of a material. You decrease the conductivity, obviously, right? It's making sense from our previous discussion. So the sigma goes down. We're not going to talk about the formula for sigma, not important. All we really understand is the higher the resistance, the lower the conductivity, the lower the resistance, the higher the conductivity. So gold, silver, copper are good conductors, hence copper wiring. Aluminum is a great conductor. You've heard of the term superconductor. Really, it's when the resistance of a material is 0, they're superconductors. Nichrome, on the other hand, I'm going to show you nichrome wiring in a minute. It has high resistance. It's not a good conductor, and that'll be the next portion. Finally, before our last example is Joule's law. Really, Joule's law measures how heat is produced from an electric current as it meets resistance or an increase in amperage. If you have a low conducting material, or if you have a material that's low in conductivity, like nichrome, which we're going to show, we're going to have an increase in heat. High resistance increases the heat from electric current, such as nichrome, which we talked about briefly. So think hair dryers, think electric heaters, right? You have an electric current flowing through wiring, which is very high in resistance. What is produced there? It's heat. And then you have a little fan flowing the heat. And that's really the essence of the hairdryer. So we mentioned that if you pass an electric charge through a material that is low in conductivity, it will produce heat, right? And we mentioned that nichrome is one of those materials that is low in conductivity. I purchased this on Amazon. It's a 30 gauge nichrome wire. And what we have in front of us is my first iteration of a foam cutter that I made. It's used for dioramas. I'm currently making a Christmas scene and I'm using foam as its base. So I needed a foam cutter to create the landscape. It's a simple contraption, if you want to call it that. We got a positive and a negative lead from a battery into the back. Got a little power switch. Positive to one end, negative to one end. Here's an nichrome wire. I've got a little spring attached just to keep the wire tight. I've got 2 power supplies here. I've got a 5 volt, 1.5 amp power supply, and I've got a 12 volt, 1.5 amp power supply. I wanted to keep the amperage the same on both power supplies. Generally use this one. It's a DC circuit. So what we're getting is 5 times 1.5 amps, 5 volt. So what we're getting is 5 volts times 1.5 amps. We're getting 6 watts of power, right? Let's demonstrate that. Let me plug this in. keep your eye on the multimeter, you'll see that we are getting 5.5 volts of power. Let's plug this into the back. And to demonstrate the heat created, we have 26 degrees Celsius, 79 degrees Fahrenheit right now is the temperature of the wire. Right, let's turn it on and let's see how the temperature changes as we're passing a 5 volt 1.5 amp current through this nichrome wire. It should generate heat. It should start to heat up. We're at 25 degrees right now. So as you can see, the nichrome wire is preventing the current from flowing through it. So it's heating up here. We're at 100 degrees Celsius. (230 degrees Fahrenheit). And just to demonstrate how this cuts, let me just try to get it on an angle here. Simply to cut the foam, as it's at 100 degrees Celsius. We have it. Let me show you now what happens when we attach this 12 volt. When we attach this 12 volt 1.5 amp power supply. So now we're getting 18 volts of power as opposed to the 7.5 volts of power from the previous power supply. Did I say 6 volts of power? Did I say 6 watts of power? 7.5 watts of power. So again, I'm going to turn off the lights here. I'm not going to take the temperature. So once you keep your eye on the wire as it heats up, keep it on the black background. See how it's glowing red? I'm not going to touch that. I'm not going to take its temperature. You see that's glowing. It's hot. So there you have it. We discussed Ohm's law. We talked about voltage, resistance, current. We talked about power and watts. We talked about conductivity. And we talked about creating electrical heat from an electrical current. Hope you learned something. Hope you'll tune back in. Hope you'll like this video. Hope you'll subscribe. Until next time. Thanks, guys. Talk to you later.